Okay, for this question you've been given a graph of y equals f of x, and we've been asked to sketch y equals f dashed x, y equals f dash dashed x. Now note that it says sketch, it's never going to be perfect, but the key things, features like stationary points, inflection points, zeros, they have to be correct. So if it was me, I would start with the sign diagram of f dashed x. So I'm going to draw that in here. So if you look at the main function, first thing you can get very easily are zeros. So zeros on f dashed x, they happen when you get stationary points on f of x. So there's a stationary point here. So it's going to, I might do that in black actually. Stationary point here is going to correspond to a zero there. A stationary point around here somewhere. If you bring that down, it can be a zero on here, and a stationary point there can be another zero. Try and get it lined up nicely. So you've got three zeros there. Now if you consider the sign of f dashed x in between those stationary points and out on the ends as well, if you look at this, all of that is a negative gradient. The pen is pointing down as we go from left to right, so that is going to be negative. Between these two stationary points it's going up, it's positive. Between these two it's negative. And between these two it is positive. So that's the sign diagram complete. Shake. So after that you can transfer, if I'm going to actually draw the thing, f dashed x on these x's, you can transfer these zeros so they're not perfectly lined up. There's one there and there and there. So you've got three zeros. So to the left of this, so all you've got is a negative gradient. So negative in the context of that, if we got f dashed x on the y-axis, a negative gradient just means f dashed x, it has a negative value, so it just means it's below the y-axis and it's going to be negative all the way through. So it's just going to do something kind of like that. I don't know how negative, it probably shallower than that, it could be like that or it could be like that. You're not going to lose a mark for that, but you need to recognise that it's going to be negative all in that section. The same, this last bit, this is just positive gradient, getting more positive, so it's positive and going further away from the axis positive, so something like that, all the way. So in between is a bit more difficult. So if you look at this section in between these two stationary points here, which corresponds to this section of the graph here, you may remember from Friday we talked about points of inflection. So you've got a horizontal gradient and it's positive, getting more positive up to a point where it gets less positive and goes to zero. So it's got to go, it's going to be in this positive region all the time, and it hangs between these two zeros. So it's got to go from here into a positive area and down again back to zero. And where the key point happens is this point of inflection. It's drawn on, it's sort of around the x-axis. It certainly doesn't have to be. In this case it probably is. But basically somewhere in between these two, that is the point of inflection where the gradient goes from increasing to decreasing. Right, so here it's positive all the way through. Here it's positive, getting more positive. You know it's getting more positive because these y values, which are f dashed x, are increasing. And here, in this section here, it's still positive. It's going towards zero, so it's going to come down like that. In between these two stationary points in here, start at zero, end at zero, getting more and more negative, point of inflection, less negative, right? So it's going to do a very similar thing. It's going to have some kind of minimum here where it gets more and more negative, as in the values are getting higher or lower, higher in number, but lower in terms of their value on the y-axis. And then they go back up to the zero. So that is a very rough sketch, but it would get good marks, of f dashed x, right? So if we use what I prepared earlier, which is probably a bit better actually, we're now going to move on to sketching f dash dashed x, and you're going to use exactly the same technique. So you see here and here, they are stationary points, meaning that the Second derivative, if that's the graph of the first derivative, then the second derivative will be 0. So I can bring those down, 0, and there's another one here, 0. So 2 zeros on f dash dash, this is the sign diagram of f dash dashed x, so the second derivative. Here, this is not helpful. This 0 doesn't really help us. What we're interested in is the gradient. Remember, the second derivative is the gradient of the first derivative. So all in here, you've got a positive line. So it's going to be positive here. In between these 2 points, negative gradient, negative, and here, positive again, just because the line's pointing up. So then, it's at either side. So that side, you just go positive above the line. Oh, sorry, I haven't drawn the axis. So hang on, let me bring that axis down. Something like that, and maybe like that. So this is going to be f dash dashed x. We know we have a 0 here, and here you've got a positive gradient in here, so it's going to be above this line, so something like that. I might actually try and dash it and make it look better later. This side is positive again, so it's probably going to do something similar. And then in between here, you've got again another point of inflection. It's probably somewhere around there, but it's going to be halfway between. If we bring that down, halfway between the zeros, you're going to have the point where the gradient, all the way through this section, is negative, but here it's negative, getting more negative, so going further down here, and then after the point of inflection, it's getting less negative and going down to 0. So it goes more negative, stationary point on here, and this. So the stationary point on the second derivative is an inflection point on the first derivative. The stationary point on the first derivative is an inflection point on the function itself. And I'm just going to finish these. So yes, whilst the actual derivative functions, this may be a lot steeper, it may end up being a lot flatter, the actual details might not be perfect, but all the key bits are right, and I would definitely get full marks for that question.